Another question to address during the development stage is whether the dataset is biased. First, we'll want to be clear about what we mean when we talk about bias. In general, it's best to understand bias as a deviation in a predictable direction, not a random one. This is important because it helps us distinguish between those errors that aren't attributable to bias. In the context of ML, bias refers to systematic errors. This oftentimes happens because biased data sets, meaning faulty, poor, or incomplete data, which can lead to a distribution mismatch between the data set and reality. Moreover, bias can not only lead to inaccurate results, but in some cases, discriminatory or unfair results, which we'll discuss more in an upcoming video. We know that if we have bad data inputs, we'll end up with bad results, and that's even if we have an otherwise perfect model. This is sometimes referred to as the garbage in, garbage out problem. But how does our data set become biased in the first place? Well, there are actually a lot of ways this can happen, ranging from conditions under which, when the data was created, how it was collected and sampled, and how it was processed. Unfortunately, bias can basically enter the picture at any point in the life cycle, making it a big challenge for machine learning. In order to tackle this challenge, I'll introduce you to some common forms of bias in data so you know what to look out for. One way bias enters the picture is owing to how we define the target variable. This gives our model an objective, but it can sometimes be a rather subjective matter, making it more of an art form rather than a perfect science. For example, if you're designing an algorithm to make promotion recommendations, how do you define a good employee? And how can you put this in terms that a computer could understand? Well, you could come up with some quantifiable measures, maybe the number of sick days, the number of times they were late to work, number of sales per quarter, and length of employment. By defining the target variable this way, we might unintentionally disadvantage some classes of people. For example, the number of sick days may disadvantage pregnant women or individuals with disabilities who are missing work. Or the number of times late to work may disadvantage those people who rely on public transportation, especially in the winter when trains or railway lines break down more often. How might this then apply to cases of TinyML? Well, imagine you're using biometric sensors for a wearable health device. How would you define someone who's healthy? Maybe you could focus on the heart rate, the blood pressure, or even the number of steps. While these seem like innocuous measures, focusing on blood pressure might disadvantage the elderly who tend to have higher blood pressure, even when they have otherwise healthy heart habits. Another way bias enters the picture is through the labeling of the data. The reason is that the labels we apply to the training data must serve as the ground truth. So as far as a model can tell, the labels perfectly match reality. But what happens when there is mislabeled data? For example, if we build a horse versus human classifier and some of the images of horses are actually mislabeled as humans, even if it's obvious to us that the picture is of a horse, the computer only knows what the picture is based off the label. So the model will start to misclassify images of horses as humans. While this example might seem easy to spot on with careful review of data, bias in labeling can sometimes be much more difficult to address. Suppose we are labeling medical images for a disease classifier, and we present a set of patient images to train graders who label the data. Even experts differ in their opinion on medical diagnostics, so we need to take their confidence or lack of confidence into account. While the two extremes of these examples might show a clear pattern, if we look at this graph over here, we'll see that there's a disagreement among the experts on which label best applies to this particular image. In which case, we have to make a controversial decision on how to label these images and to train our model moving forward. Another form of bias relates to how we sample the data when we are using it to train. Imagine we are training a model to respond to a wake word, and our data set looks like this, with mostly white individuals. Now, let's suppose that the data doesn't accurately represent reality, where users are significantly more diverse. And we will end up, what will end up happening is that our model will perform less well for individuals who aren't represented in the training data set. Bias may also, be a result of prejudice or historical injustices reflected in the past data. For example, Northpoint relied on an algorithm to predict the recidivism risk, that is the tendency, of a convicted criminal to reoffend. And despite, equal accuracy in terms of correct predictions, Black defendants were almost twice as likely as whites to be labeled as higher risk, but not actually, reoffend. And the opposite mistake was made among whites, who were much more likely to be labeled as lower risk, but go on to commit other crimes. This is attributed to historical injustice in policing practices that have been disproportionately focused on minorities, resulting in a higher, arrest rates among these populations that gets reflected in the data set. And then this sort of unfortunate thing continues even when we apply machine learning. This type of bias, may also occur when stereotypes skew the data sets. For example, the stereotype that women are primarily responsible for cooking and other household chores might result in women being overrepresented in a data set that includes images of people cooking. This could cause the algorithm to be inaccurate by predicting women are cooking a majority of the time, even when it's, isn't actually the case. Bias can also be attributed to measurement distortion. This most often occurs when there's a problem with the device making a measurement or the observation. To put it simply, hardware in this case really matters. For example, optic sensors and cameras have a problem detecting darker skin tones due to the way light is reflected. And this has led to notable issues with, even simple things like automatic soap dispensers, or, during these COVID times, finger pulse oximeters have difficulty in reporting with darker color skin. And tools for, even activity detection and facial recognition all have issues based on skin tone. Additionally, this can happen when the device used to collect the data for training differs from the device that is used when the model is actually deployed. If our data set contains images taken from, digital SLR cameras, and the device our model is deployed on is a mobile phone, as in these images show, the value distortion will cause the model to generate bad results. So let's understand, how can we fix biased data? One industry solution called Datasheets for Datasets was published in a paper by researchers from Google and Microsoft, as well as academics. They offer a list of questions for dataset creators to reflect on during the key stages of the dataset lifecycle. For example, what's the motivation of creating this dataset? What's the composition and what is the collection process? And what kind of pre-processing was used? And then how are these labels actually assigned? And then in terms of how the data set is used, how it's distributed, and how it's maintained over its life cycle. Similarly, the data nutrition project suggests data nutrition labels, a standard label that highlights key ingredients of the data set, like provenance, where did the data come from, metadata, missing units, and so forth. This helps someone at a glance get a better sense of what the data contains, and make more informed decisions about whether it's an appropriate data set to use for their project. There are also bias testing toolkits coming out. For example, IBM offers an AI Fairness 360 tool that makes bias testing a part of your development cycle. And similar tools are offered by Google and Microsoft. Now, just to wrap up, as an individual designer, there are some helpful tips to keep in mind to mitigate bias. First, carefully research your users in advance and be aware of potential outliers in your user population. Ensure your team of data scientists and data labelers are actually diverse, right? Have a measure of their diversity. Where possible, combine inputs from multiple sources to ensure data diversity. Don't just get it from one country or one kind of set of sensors in one environment. Try to vary that. Create a gold standard for data labeling and create that as a best practice that is shared among data labelers. And then seek out domain experts to review your data and get their inputs and see where disagreements are when you're trying to make these controversial decisions. Now that you're familiar with the problem of biased data sets, you're one step closer to developing reliable and accurate TinyML systems.